Welcome back. In this video, we're going to see the squeeze theorem again. That's why this is called squeeze theorem revisited. No new vocabulary, but we are going to see a pretty big theorem about the properties of limits as x approaches positive or negative infinity. So, the squeeze theorem also holds for limits as x approaches positive or negative infinity. Now remember, we know the squeeze theorem as the theorem that says if we can fit a function in between two other functions at some c value, some constant value, and if the limit as x approaches that constant value of g of x is the same as the limit as x approaches that c value of h of x, and those are both some equal limit, then the limit as as x approaches c of that squeezed in between function is also L. In graphical form, generally what we do is say, well, here's our function, and then we have, a function that lives entirely above, and we have a function that lives entirely, that's in yellow, below, and we try to squeeze it in. So this is all taking place at some constant value. We're going to say the squeeze theorem holds true as x grows large if we can squeeze some function in between two others. So here's our example. Find the limit as x approaches infinity of f of x for this function, the sine of x over x. So I think the first thing we should do is examine this function graphically. So let's take a look at Desmos. Here it is, the sine of x over x, and we see that this function oscillates back and forth above and below the x-axis, but it does seem to flatten off as things get big. So we can go back home here, and then I even put up a table, and we can show, okay, so what happens at 10, what happens at 100, what happens at 1,000. Look how close we're getting to 0. So I'm pretty sure by both graph and table, I know what the limit is. I'm going to even write it down here. The limit as x goes to infinity of the sine of x over x is 0. But how can we show this with the squeeze theorem? Well, we know that the sine function lives between -1 and 1 at all times. So for all x greater than 0, or all x positive, we can say this. We can start with this very statement and kind of divide through by x. -1 over x is less than or equal to sine of x over x, which is less than or equal to 1 over x. And our function here is our f. The function to the left or underneath is the g, and the function over here is the h. And we have the limit as x goes to infinity of -1 over x, the same as the limit as x goes to infinity of 1 over x. And we know that both of these are 0 from the previous video. Therefore, the limit as x goes to infinity of the sine of x over x is also 0, and the squeeze theorem remains the same. All right, here's a theorem. Properties of limits as x approaches positive or negative infinity. Let's let L, M, and K be real numbers. L, M, and K are real numbers, and the limit as x approaches both positive and negative infinity of f of x is that real number L. When x approaches positive or negative infinity of g of x, we've got m. So the sum rule. Turns out that if we add two functions in a limit, that limit is the sum of their limits, f and g. Same for differences. We have the difference of the limits. Same for products. If we're multiplying two functions f times g in a limit, then the limit is the product of their limits. Constant multiples. If we have some constant k times our function, then the limit is that same constant k times whatever the limit of f of x was. Sometimes we even look at this as factoring out the k and multiplying it by the limit. Quotient rule looks a lot like the product rule, as long as that denominator is not 0. And finally, the power rule. This one comes up from time to time, and it's almost like we can say, all right, well, whatever the limit as x approaches infinity of that function was, take that limit and apply the power there. So with that in mind, let's use that property and figure out what this limit's going to be. Find the limit as x approaches infinity of 5x plus sine x all over x. Okay. Well, here's what I might think about doing. This looks to me like a sum. So what I'm going to do is kind of break the sum apart into its two pieces and rewrite this as the limit as x approaches infinity of 5x over x plus sine x over x. Okay. Then the sum rule says I can do limit as x goes to infinity of this first piece. So 5x over x is 5, plus the limit as x goes to infinity of sine x over x. So the limit as x goes to infinity of 5 is just 5. And the limit as x goes to infinity of sine x over x we now know is 0. So this whole limit is 5. So hopefully that worked out pretty well for you. And I will see you back in the next video.